searing heat, freezing ice, monsoon rains and dusty droughts, spring, summer, autumn, winter. For hundreds of millions of years, they have defined the rhythm of nature on our planet. They underpin the daily existence of billions of us today. A product of the clockwork of the heavens, these are the seasons of planet Earth. When talking about climate, one cannot ignore the concept of the seasons. It's the variation in temperature and precipitation throughout the year that defines each climate zone on our planet. Each zone has a unique combination of seasonal patterns, and these patterns determine the biome, the characteristic of vegetation of the land in that zone, what agriculture can be sustained there, and ultimately whether it can support human population. But what are the seasons? What is their origin? Why do they always repeat year after year? Why are they different in the tropics than in the higher latitudes? And why do they reverse in the southern hemisphere? All these questions are answered in the relationship between our planet and its parent star, the Sun. When a planet orbits a star, it traces an elliptical path that is always in the same horizontal plane, the orbital plane. But the planet itself will rotate on its own axis at some other angle, what is known as axial tilt. The result of this is that as the planet moves around the star, the angle at which the star's light strikes any particular point on that planet will change. As surface and atmospheric heating is directly related to the angle of the star's light, the position of the orbit will therefore influence temperatures for that region of the planet. So every planet in the galaxy with an atmosphere will have some combination of seasons. And so the phenomenon shouldn't be thought of as unique to our planet. In fact, the planets Mars, Saturn, Uranus and Neptune, and Saturn's moon Titan all have distinct seasons that have been observed. There are 4 significant points in any planet's orbit in this regard. The first 2 being when each of the planet's poles is pointing closest toward the star, and the second 2 being when the poles are exactly at right angles to the star. In the case of our planet, our axial tilt is just over 23 degrees. So on the day when the North Pole is facing closest toward the Sun, June 21st to be precise, every point on a line encircling the Earth 23 degrees north of the equator will experience a midday sun that is exactly overhead. This is midsummer in the Northern Hemisphere, when heating from sunlight is at its greatest. Exactly 6 months later, on December 21st, when the South Pole is facing closest toward the Sun, every point on the Earth 23 degrees south of the equator will have a noonday sun overhead. This is midsummer in the Southern Hemisphere. These 2 lines are respectively the Tropics of Cancer and Capricorn, called such because the Sun is in those zodiac constellations on those special days, which are known as the summer and winter solstices. The word solstice comes from Latin sol plus stit, meaning sun stationary, and literally describes the stop and reversal of the Sun's highest or lowest daily point in its seasonal progression. Exactly in between the solstices, on March 21st and September 21st, the Earth's poles are at an exact right angle to the Sun, which means that on these days the Sun at noon at the equator is directly overhead. These days are called equinoxes, from the Latin equus plus nox, meaning equal night. The hours of day and night across every point on Earth are the same at 12 hours each on these special days. In practice, midsummer temperature peaks lag behind midsummer's day by a month or so. Most will experience that July and August are the hottest months in the Northern Hemisphere and not June, and the same goes for winter, with January and February being the coldest and not December. This is called seasonal lag, and occurs because it takes time for the Earth and oceans particularly to warm up in that area. This cycle repeats itself near exactly, year in, year out, because the Earth returns back to the same point exactly 1 year later, as regular as clockwork. If human-made clocks could ever be so precise. I say near exactly because the Earth is in fact wobbling by a few degrees on its axis in the same way that a spinning top might wobble. But this wobble has a cycle of almost 26,000 years, so you're not going to notice anything in your lifetime. Okay, so that explains the origin of the seasons. But the effects of this on daily weather depend upon whether you live inside or outside the tropics of Cancer and Capricorn. Within the tropics, the changes in the angle of sunlight from one solstice to the other has little to no influence on surface heating, and so the tropics see very little change in temperatures across the year. Seasons in the tropics are in fact determined by the presence or absence of rain. When the sun is at right angles to the Earth, heating is at its greatest, leading to thermals of hot, moist air which, when rising into the upper atmosphere, cool, losing their moisture and depositing rain in the form of thunderstorms. As the sun tracks back and forth across the equator throughout the year, this band of rain follows it. This band is called the doldrums, or the intertropical convergence zone, as it is the convergence of tropical winds known as trade winds being sucked into it from surrounding areas. When these winds carry moisture, they also bring rain, and so this complex pattern determines what areas will be wet or dry during what season. Only where the ITCZ is stable, or where the trade winds carry moisture regardless of direction, do we have the tropical rainforest, where rainfall and temperature are near constant throughout the year, the only climate on Earth without seasons. Outside the tropics though, these sunlight angles become more important. If you know anything about trigonometry, then you'll get the idea that as the angle of sunlight to the surface becomes shallower, there is an acceleration of the effect of that heat being spread out across the surface and being diluted in power, so that by the time you reach the poles, the heating effect of the sunlight is only a tiny fraction of what it is at the equator. In the Mid Latitudes, the change in seasonal angles is significant enough to produce large changes in temperature. In summer, the sun is high above the horizon, concentrating heat and delivering warm or even hot days. In winter, it's much closer to the horizon, and so surface heating is much less, with the result of significantly colder days. This variation in temperature in the mid-latitudes is diluted, however, by the proximity of oceans. Being a large fluid mass, kilometers deep, the oceans do not heat as much in summer as the land, and do not cool as much in winter. So land areas near an ocean have much smaller winter-summer temperature ranges than those in the continental interior. This difference in coastal and interior continental temperatures is at its greatest in the mid-latitudes and is the essence of why we have more climate types in this region of Earth than any other. In the polar regions, the effect of axial tilt is at its extreme. Above the polar circle at 67 degrees north, there is at least one day each winter when the sun does not even climb above the horizon, and at least one day each summer when the sun never sets. As one approaches the pole, these numbers of days increase until at the North Pole, the sun doesn't rise for 6 months in winter and stays above the horizon for 6 months in summer. The same occurs at the opposite time of year in Antarctica. In the Koppen climate classification system, we have categorized patterns of temperature and rainfall determined by the seasons. You can learn more about this in my intro video, linked top right, or by watching my Secrets of World Climate series, which covers each zone in detail. What you almost certainly haven't seen before is a representation of seasons across all Koppen climate zones in one image. And here it is. For readability, I have grouped similar zones together or omitted rare or isolated ones. This list shows the most important and distinct zones, starting at the equator at the top and finishing at the pole at the bottom of the page. For each zone, I have depicted the change in temperature across the year in a color spectrum, from red as the hottest to purple as the coldest. Below each temperature progression is a progression of precipitation, with rain in blue, snow in white, and intensity of such precipitation as proportional shading. These patterns are for the northern hemisphere and will naturally be reversed for the southern. I have provided a link to the high-resolution version of this image in the notes accompanying this video, so you can pore over it at your leisure, but for now I will highlight the most interesting features. Up top, we see the unchanging, single hot and wet season of the tropical rainforest. Next, we see the change in rainfall across the year in the tropical monsoon and savanna climates, with a slight bump in temperature just before the wet season. After this, we see the unique subtropical highland climate where temperatures are reduced due to altitude. Note that there is a form of this climate where the rain is constant year-round, but is not shown here. Then we come to the hot desert, where there is little to no rain, but intensely hot conditions in summer. We then have the unique three-season climate of the subtropical monsoon, a mild dry winter and then a short and very hot dry summer, followed by a hot wet season. As we move into the mid-latitudes, we get our first cool winter temperatures in the humid subtropical, followed by the unique dry summer, wet winter pattern of the Mediterranean climate zones. This latter, together with its westerly ocean-facing sibling, the oceanic, demonstrate mild temperature ranges from winter to summer. By contrast, the continental climate zones that follow show much more extreme temperature ranges, with subdivisions of these being the cool deserts with absence of rain, humid continental where we see snow and rain defining seasonal precipitation, and continental monsoon where this pattern is varied by an absence of winter precipitation. The final continental climate of the subarctic is then seen with extreme temperature ranges featuring very cold winters yet warm summers. And as we reach the poles, freezing temperatures dominate, with only a brief cool summer in the tundra bringing any respite to these forbidding lands. And so there we have the seasons of planet Earth. I hope you found it enlightening in answering your questions about the changes throughout the year that affect us so much. If you haven't already subscribed to my channel, please do so now so you don't miss future episodes, and please click the like button and share with your friends if you found it useful. Thanks again for watching, and I'll see you soon in the next chapter of my climate casebook.